Hey guys, welcome back to another video. So in this video, I wanted to introduce another strategy that we can use in order to solve first order differential equations. So whenever I introduce a new strategy, I always like to give a recap on what we've learned so far, just so we can keep things in perspective. So far, we've looked at separable differential equations where we could isolate the x's with the dx and the y's with the dy and then straight up integrate. And we also looked at non-separable differential equations in which we would have to find an integrating factor and multiply through the whole entire equation and then solve from there. In both of these forms, we have focused on y prime plus a of xy is equal to b of x. So what if our differential equation is non-separable, or it's nonlinear, or it doesn't fit this form and we don't have a way to solve this? For example, let's take a look at this differential equation right here. Using what we've learned so far, I would try to manipulate this into either a separable or a non-separable differential equation of this form so I can solve it. But I can see that if I rewrite this as y prime is equal to x squared plus y squared divided by xy, and I multiply over this xy, so I get xy times y prime minus y squared is equal to x squared, I can see that this is in fact a nonlinear differential equation. And because it's nonlinear, I don't have the tools or strategies to solve this. So in this video, I want to point out that there is a class of differential equations in which we refer to as homogeneous. And one of the things that makes a differential equation homogeneous is if we can express the differential equation, the first order differential equation, in terms of a function of our function that we're solving for divided by the variable that it is a function of. So if I can rewrite our differential equation in terms of the fraction y over x, then I can solve this using a homogeneous strategy. All right, so let's take a look at this differential equation. And what we want to do is we want to express this whole entire right-hand side as a function of y over x. So how can we do this? Well, if we divide both sides of this fraction, the top and bottom of this fraction, by 1 over x squared, then what I get is x squared divided by x squared plus y squared divided by x squared all over xy divided by x squared. And what this simplifies to is 1 plus y over x quantity squared divided by y over x. So I can see that I have successfully manipulated this differential equation into a form that basically puts it into only a function of y over x. So the next thing that I'm going to do is I'm going to make a change of variables. I'm going to make a substitution. And we'll call it v. And I'm going to let v equal y over x. And therefore, x times v is equal to y. And if I were to differentiate both sides with respect to x, then using the product rule on this left side, what I get is v plus x dv dx. And we get this term right here because v is a function of x since y is a function of x. And on the right-hand side, we get dy dx. So basically what this gives us is this gives us an expression for dy dx, and this gives us an expression for y over x. So we're going to substitute in these two expressions into our differential equation. So what we are left with is dy dx is equal to v plus x dv dx. And this is equal to 1 plus y over x squared over y over x, or in other words, 1 plus v squared over v. And now what we're going to do is we're going to start dealing with this differential equation. Okay, so here we have the differential equation from the previous step, and this represents the substitution that we made, and I'm going to keep track of this. I'll keep this hanging out right here. All right, so I'm going to move this v onto the other side by subtracting. So I'm going to write it like this. And now what I want to do is I want to get this all under a common denominator. So I'm going to rewrite this as x dv dx, and this is equal to 1 plus v squared minus v squared divided by v. And this comes out to be 1 over v. Again, this is just simple algebraic manipulation by getting a common denominator. So now my differential equation reads x dv dx is equal to 1 over v. And now I can see why this idea of a homogeneous differential equation with this change of variables is important, because we basically turned a nonlinear differential equation that we started with into a separable one, because this is separable. I can multiply this v over and I get v dv is equal to 1 over x dx, and now I can just straight up integrate both sides. And when I integrate v, what I get is 1/2 times v squared, and then plus a constant of integration. And when I integrate the right-hand side, what I get is just the natural log of x. So now I'm going to come back to our original substitution, which we said v was equal to y over x, and I'm just going to substitute that back in. So since v is equal to y of x, I'll rewrite this as 1/2 times y over x squared plus c, and I'm going to set this equal to the natural log of x. So now all we have to do in order to solve this equation is just solve for y. So after a little bit of algebraic manipulation, what I get is y over x squared is equal to the natural log of x minus our constant, and then all multiplied by 2. And then I can take the square root of both sides and multiply over by x, and what I'm left with is y is equal to the square root of 2 times the natural log of x plus an arbitrary constant, where this constant absorbs the negative sign and the factor of 2. Since it's arbitrary, I'm just going to write it as c. And then all of this times x. So this would be the solution to the differential equation that we started with, which was dy dx is equal to x squared plus y squared divided by x times y. And notice how we used a change of variables by letting v is equal to y of x, y over x. And we use this change of variables in order to turn this differential equation right here into a separable one. And then we changed our variables back, and what we got is a solution expression for y. So this strategy works for homogeneous differential equations where we can express the function, this side of the equation, we can express this term as a function of only y over x. And if we can do that, then often we can take advantage of this change of variables, v is equal to y over x, and we can turn it into a separable differential equation in which we have the tools and strategies to solve. So anyway, thanks for watching, and I'll see you guys in the next video.